Hey everybody, so brand new topic in this video. We're going to start analyzing trusses. So imagine you have a structure like a bridge or the frame of a house, especially the frame of a roof. You have a structure that looks sort of like this. Now let's make some assumptions, some idealizations to make the analysis a little bit simpler. So assumption 1, let's assume the load on the structure, let's say this, is much larger than the weight of each of these individual beams. If that's true, then the weight of each of these beams becomes negligible compared to the actual load acting on the structure. So that makes analysis much simpler. We can just neglect the weight of each of the members of the structure. Okay, second assumption. Let's assume that each of these joints is just a pin support. So in reality, if you take a look at this, the joint of this bridge, it's actually welded here, and some places are riveted. So for example, see this beam right here? If I apply a torque here, there's going to be a reaction at the weld. Here, there's going to be a reaction torque at the weld. But if we assume it's just pinned here, then when I apply a torque, the beam will just rotate. There wouldn't be any reaction torque at the pin. So that will make analysis much simpler if we just assume pins and no torques at the joints. And it's somewhat justifiable because the forces in this direction and this direction are larger in magnitude than the torque in this direction. Okay, so the side effect of having no torque at the joints, let's say I take one of these and I just draw it by itself, free body diagram, then there would be reaction forces at these joints, but no torque, nothing like this. Now, if this member is static, like the members of the structure aren't accelerating in all directions, it's just static. If the acceleration is 0, then this force has got to be equal and opposite this one. This one has got to be equal and opposite to this one, which means we have one of two scenarios. Either the reactions at the joints look like this, or the reactions at the joints look like this. Right? They have to be along the axis of that beam, which is to say that they are axial forces. Axial meaning along the axis. Okay, and then when they're toward, like this is compression, and like this is tension. It's like smashing it or stretching it. And when you analyze trusses like this, you have to specify your answer as being either tension or compression, because we might not know how you did your analysis if you drew your forces like this or like this. Did you draw your forces going toward the joint or away from the joint? For example, let's say you have an airplane and a submarine, and here's sea level. Let's add some little bit of detail. So here's the airplane, and here's the submarine. Okay, so if you ask, let's say the airplane pilot will be like, I'm going to say upwards is positive. And the submarine pilot will disagree and say, I'm going to pick my coordinate axis where down is positive. So the airplane pilot will say 30,000 feet or negative 10 feet. 30,000, if up is positive, means 30,000 feet above sea level. If up is positive, negative 10 means the plane crashed into the ocean and is 10 feet below sea level. But let's say for the submarine pilot, 1,000 feet or let's say negative 10 feet. 1,000 feet, if down is positive, means 1,000 feet below sea level. But if down is positive, negative 10 feet means like the submarine ran aground and is 10 feet above sea level. Okay, so if you say 10 feet, do you mean 10 feet above sea level or 10 feet below sea level? We're not sure if you're an airplane pilot or a submarine pilot. So same story. When you analyze structures, when you write your solution, you say maybe like your answer is 10 newtons. Do you mean 10 newtons tension or do you mean 10 newtons compression? So you have to specify. Okay, and we will go over 2 different methods to analyze trusses, method of joints and the method of sections. So let's start with what I consider the more systematic of the 2, the method of joints. So here's how it works. So this truss, it's all pin supports at the joints, but then the entire structure is supported, like it's against this wall here. And then there's a pin support, this one right here, this is a pin support at A, and a roller over here at B. So you just go joint to joint, draw the free body diagram. So let's say for joint A, imagine you kind of cut it like this. So like this. So for joint A, here's joint A, like there was a bar here and a bar here, but I cut it like this. So then there is an axial force either this way or this way. So it's up to you to decide which way to draw it. The convention, I'll tell you now, is out, meaning the convention is that tension is positive. So let's just stick to that convention. So tension here, and then it's between joints A and C, so I'll just write tension. I'll write T for tension, and then that's between joints A and C, so I'll just write AC. And then here, there's tension, and between joints A and B, so I'll write T for tension between joints A and B. Now, if I get an answer that is positive, let's say this is 5 newtons. The answer is positive. That means for axial force AC, it's 5 newtons in tension. But let's say for this one, I get an answer that's like -3. That means for axial force AB, it was actually 3 newtons in compression because I drew my arrow in tension, but I got an answer that was negative. Okay. Let's finish the free body diagram. So there's the pin support. So for example, if I pick coordinates like this, then the pin support has some reaction force, which I would decompose into X and Y components like this. So it's some 2-dimensional force. I don't know which way it's going, so that's why I decomposed it into X and Y components. And the way you decompose it will just depend on how you pick your coordinates. So any 2 of you could have different choices for coordinates. So let's say if I pick coordinates like this instead, then for reaction force A, I'll decompose that into my choice for X and Y, like this. Okay, so here's the free body diagram for joint A. Now, let's write Newton's laws, decomposed into the components based on my choice of coordinate. Let's see, I need to know a little bit about the geometry. So there's some angle here, which is the same as the angle here, same as the angle here. So I'll just call that angle theta tangent. Theta is opposite over adjacent. So 6 over 10. Okay, so then theta is known, arctangent of 6 over 10. So we know this is known. Okay, and if x is here, the x component of this, cosine, and then the x component of this, nothing, nothing, and this. Okay, y direction, I got this one. This is going in the negative y direction. And then the y component of this, negative sine. Okay, so I have 4 unknowns, 2 equations. I can't solve it. So the technique is we go to the next joint. So let's say joint B here. So now I draw the free body diagram of joint B. So there is joint B, and then there is that beam going up this way, and then the one going at this angle over here, then over here. Okay, so the one going up is between joints A and B. The one going at that angle is between joints B and C, and then the horizontal one is between joints B and D. And I drew all of my arrows going out in tension. And then let's not forget that there's the roller support here. So there's got to be a reaction here from the roller support, which only has an x component. So here we go. Let's write Newton's second law for this one. Okay, so x direction. Let's see, also there's an angle here, which is arctangent of opposite over adjacent. So arctangent of 3/5, which happens to be the same as arctangent of 6 over 10. So it's actually the same angle as this one. So I'll just write theta. Okay, so x direction. This, and this. Okay, y direction. Okay, so all together we have 4 equations and how many unknowns? 1, 2, 3. These are the same unknown. 4, 5, 6, 7. 7 unknowns, 4 equations. We don't have enough equations, so then we go to the next joint, joint C. So joint C, the free body diagram looks like this, and this is between joints A and C, joints B and C, joints C and D, and the geometry happens to be, the angles are like this. There's some symmetry here. This angle is the same as this angle, is the same as this angle. Okay, so now Newton's laws. So you see the pattern in the method emerging in the x direction. I'm using this choice of coordinates. Negative t AC cosine minus t BC cosine plus t CD cosine. Okay, y direction, TAC sine minus TBC sine minus TCD sine. Okay, so now we have 2 more equations, but by doing that we introduced yet another unknown. So we still don't have enough equations for the unknowns. Note that this TAC is the same magnitude as this TAC. This TBC is the same magnitude as this TBC. Okay, so now we need to move on to the next joint, joint D. So you see, here's joint D, free body diagram looks like this. 2 kilonewton load here. This is between joints C and D. This one is between joints B and D. And this angle is arctangent of 3 over 5. And again, 2 equations, right? X direction minus TBD minus TCD cosine. Y direction, TCD sine minus the 2 kilonewton load. Okay, now we have 1, 2, 3, 4, 5, 6, 7, 8 equations. How many unknowns? TAC, TAB, TBC, TCD, TBD, and the reactions at the supports. So we have 5 axial forces in the members of the truss and 3 reactions at the supports. 8 unknowns, 8 equations you can solve. So this method is well suited for computers because you just give it 8 equations, 8 unknowns. But it's not as bad as it sounds, because realistically, how do you solve this? Look at the free body diagrams. This has 4 unknowns. This has 4 unknowns. This has 3. This has 2. Where should you start? Start with the fewest unknowns. This one. It has 2 unknowns, and we have 2 equations, which means if you start here, 2 equations, 2 unknowns, means you know both TCD and TBD. You have both of them. So you have the answers, CD and BD. So these are known once you solve these 2. And then you go on to the next one. Here has only 3 unknowns, but we just solved this one. So now there are only 2 unknowns left, here, and we have 2 equations. So then you move on to one of the others. Again, we know TBC, which is this, TAC, which is this, and see right here, TBD, that's right here. Okay, so now look at this. This has 3 remaining unknowns. This one only has 2 remaining unknowns. And we have 2 equations, which means you can solve these 2 unknowns with these 2 equations. And now you know this, which is this. So if you look, there are only 2 remaining unknowns, and you have 2 equations. So that's how it's really systematic. You just go joint to joint, write 2 equations for each joint. Once you do that, then you can go back and solve for everything. Okay, so practice this. Let me show you an alternative method. Let's maybe put this in a separate video. So I'll see you on the next video.